I will give you the constant, so I'll say the speed of light is 3 times 10 to the 8th. And Planck's constant is 6.626 times 10 to the negative 34th. So this is the speed of light, which is 3 times 10 to the 8th meters per second. And h is Planck's constant. Yeah. But you need to know the equations. I'll give you the constants, but you need to know the equations, okay? And we have 6.626 times 10 to the negative 34th.
So you'll give us that?
Yes, I'll give you that number. Yep. I'll give you Planck's constant and the speed of light. And what does this lambda stand for? And that's in meters. And how about V? Frequency. Which is in hertz. Same with this V2. This V is frequency also, and then E is, yep, energy. And that's in joules. Yep. And remember, the wavelength has to be in meters, and 1 meter is equal to 1 times 10 to the 9th nanometers. So if you have like 610 nanometers, yep. 1 times 10 to the 9th nanometers in 1 meter. Okay, the line emission spectrum. We have brightly colored lines. That correspond to wavelengths. And the line spectrum is unique to each element. Just like the color that we saw in the metal, the flame tests were unique to each of those metals. And why is the light emitted? Yep. So when electrons move from excited state to ground state. So it has to absorb energy of some form by heat or electricity, move to excited state, and then when it drops back down, it's going to release light. Next, the quantum numbers. We have 4 quantum numbers. We have principal, the quantum number. What does that describe? Yep. back. That little n is the letter they use, like n equals 1 or n equals 2. Energy level. Next one is angular momentum. Which is L, our L value. What does this describe? Yep, the shape. The shape of the sublevel. Yeah, but like when you're talking about S, P, D, and F, those are called sublevels because they have individual orbitals, but the orbitals have different shapes too. And this L can equal what? 0, 2, and minus 1. And we had this chart where if we have L values, like if our L is equal to 0, what shape did that, or what letter? And if L is 1, that's P, 2 is D, 3 is F. If L is what? Yep, you can only have one sublevel. So if n is 3, you have L can equal 0, 1, and 2, so you have 3 different sublevels that are possible if you need to fill that far, S, P, and D. Magnetic. Which is ML. And what does that describe? Yep, orientation of the orbitals. So ML can equal what? Goes from negative L to positive L, including 0. Like how P has 3 orbitals, and they're oriented around the nucleus differently. So we had this oriented on the x-axis. Like this. They're all the same shape. They all have 2 dumbbell, or the dumbbell, 2 lobes. The orientation is whether they're which axes they're on. And the number of ML values is equal to the number of orbitals. Like when L is equal to 1, when we have a P sublevel, that's a L value of 1. We have a negative 1, 0, and 1. So that's 3 ML values, so we have 3 orbitals. And then the last one is the spin quantum number, which was, oops, MS.
What was the last part you put on ML? Number of ML values equals number of orbitals.
Yes. And this describes the direction of electron spin on its axes. So not like it's spinning around the nucleus in a certain direction, because they can take random paths. They don't have to be in a certain path. But it's spinning on its axis like the Earth spins on its axis. And so ms can equal what? Yep. So you have two values. They have to have opposite spins, which is why there's 2 electrons per orbital.
How do you decide whether?
It doesn't, unless it specifically tells you, and I don't think anything would ever tell you that's going clockwise or counterclockwise. So. That's what I would say. I don't know. I don't know that it really has been determined. Yep, you just get to pick one. Okay, I think that's all of them. So if I said, if you have a (4p) sublevel, what is a possible set?
Are you doing the whole thing? Whole possible set?
Yep, one possible set of 4 quantum numbers.
4, 3.
So this is in the ML, MS. So I want one of those. So what's N? 4. What's L? 1. Because it's P, because it's a P orbital, P is 1.
P is 2, so then it's minus 1.
No, P is, L value is 1. P's L value is 1. Yeah.
And what's
So ML can be what? What are the possible values for ML? Yep, so you have negative 1, 0, or 1. So which one do you want to pick?
0.
Okay. Yep, and you just pick plus 1/2 or minus 1/2. And there you go. There's a possible set.
So your N is always just whatever that like.
Yes. Okay, next one, electron configurations. I'll put a couple up here and you guys tell me what the configuration is. Oops.
Fluorine.
Nickel. One S2. 2s2, then what?
2p6, 3s2, 3p6, 4s2.
Eight. Yep. You want to go through another one? We'll do one more. I heard a couple yeses.
Potassium.
Sodium.
Sodium.
1s2.
2s2, 5p6, 3s41.
Yep. And so this is where you might have questions like what we did for the science starter. How many electron-containing orbitals would there be? How many completely filled orbitals?
Can we do the orbital notation? Would we do the orbital notation?
Yes, well,
The orbital notation.
the very,
How many
the
orbitals?
very bottom is orbital notation.
Well, if
You
say
don't
how
have,
many-
you wouldn't have to draw it out because you should know that everything's full up until the last one, right?
Okay.
So you can just count how many orbitals there would be. There's 1 here, 3 here, and now, well, S is pretty easy because there's only 1 orbital, and it has 1 electron, so it'd be 1. How about this one? Would this one be completely full?
There'd be 2 then.
It's not completely full, so we'd have 1, 2, 3, 4, 5, 6, 7, 8.
So if they ask for how many are completely filled, it'd be 1, 2, 5, 6, 10, 11, 13, 14.
13, isn't it? 1, 2, 5, 6, 9, 10, 13. Yep, 13 completely filled. Two lone electrons here, no empty orbitals. Yep.
And you'd have an empty one if it was like 3D3.
Okay, noble gas configuration. So let's write out europium. Europium's number 63. So what? Xenon, yep. And so after xenon, it's the noble gas that came before europium. Europium's number 63. So we
6S2. And then 5D1.
Yep. And then
4F6.
so any of them that are that far down in the periodic table, I'm pretty sure you would have the noble gas configuration, not the whole thing.
Yeah, so we'd be right here.
Okay, the orbital notation then for, let's do magnesium. So magnesium, we have 1s and how many electrons? 2. Actually, let's not do magnesium. Let's do silicon.
If you've already
Silicon. Okay, and then we have 2s, 2, and there's 1 orbital, so we'd have 2s.
why can't we do magnesium?
Ooh, what's wrong? I did something wrong here.
You put 2 up arrows.
I did.
Yeah, that's defying Pauli exclusion.
Yeah.
Come on, this leader.
P, 2p has how many orbitals?
3.
And there's 6 electrons. Comes after 2p.
3S.
So 1, 2. 3p has 3 orbitals since it's a p sublevel. How many electrons? 2. Right. And do I put them both on the same orbital?
No, that's not Hund's rule.
Yep, we gotta follow Hund's rule and have 1 electron in each orbital. Yes, you should label each orbital. Maybe like a fraction. Okay, any questions for the whole chapter? Yep.
So, ML,
Uh-huh.
or, yeah, ML,
Uh-huh.
is you just use always -1, 0, or 1.
If L is 1. If L is 2,
It's -2, 2.
-2, -1, 0, 1, 2.